Welcome everyone. In this lesson, we are going to study the common base amplifier, one of the three basic amplifier configurations you will meet in electronics alongside the common emitter and common collector configurations. We'll analyze it using the H parameter model, which treats the transistor as a small linear two-port network defined by 4 parameters. By the end of this lesson, you will be able to work out the current gain, voltage gain, input impedance and output impedance of a common base amplifier from first principles. Let's look at what you should be able to do after completing this section. First, describe and analyze the operation of a common base amplifier using the H parameter model. Second, determine the voltage gain and explain why there is no phase inversion between the input and output signals. Third, discuss and calculate the input resistance. Fourth, determine the output resistance. Fifth, determine the current gain. And sixth, determine the power gain. Keep these 6 objectives in mind as we work through the derivations. We'll cover each one in turn. Let's start with the common base configuration itself. In this circuit, the base terminal is common to both the input and the output. It's held at a C ground by capacitor C2. So as far as the signal is concerned, the base doesn't move, it's fixed. The input signal is capacitively coupled into the emitter, and the output is capacitively coupled from the collector to a load resistor RL. Now, why does this configuration matter? It comes down to impedance matching. Impedance matching means arranging a source and a load so that signal or power transfers efficiently between them. For an amplifier, we generally want the input impedance to suit the source and the output impedance to suit the load. If the impedances are badly mismatched, the signal voltage can become very small or the power transfer can be poor. It's worth noting that impedance matching does not always mean making the two impedances numerically equal. That's only strictly true for maximum power transfer. For many voltage amplifiers, what we actually want is a high input impedance and a low output impedance. But the common base amplifier is particularly valuable when the signal source itself has a low impedance, especially in high frequency and RF circuits such as an antenna or a low impedance microphone. As the diagram on the right shows, a common base stage is often used as the first stage in a cascade, precisely because it presents a low input impedance to match a low impedance source and a high output impedance that can then feed a voltage amplifier stage. So to summarize, a common base amplifier has a particularly useful impedance combination, low input impedance at the emitter and high output impedance at the collector. Now let's build the small signal AC equivalent circuit to do this. We replace all capacitors with short circuits, since at the signal frequency they behave as if they aren't there. We also connect the positive terminal of the DC voltage source to ground, because a DC supply is effectively an AC ground. As a result, R1 and R2, the biasing resistors, vanish from the AC circuit entirely, since they are now simply connected between ground and ground. What we are left with is the H parameter equivalent circuit shown on the right. The input side has a voltage source Vs feeding the emitter through HIB, and the output side has a current controlled current source HFB times IE feeding the collector along with the output conductance HOB and the load resistor RL. For this example, we'll use typical common base amplifier values. HIB equals 30 ohms, HRB equals 4 times 10 to the negative 6, HFB equals negative 0.99, HOB equals 8 times 10 to the negative 7 Siemens, and RL equals 20 kilo ohms. Using these values, we are going to find 4 things. Part A, the current gain ratio AI, part B, the voltage gain ratio AV, part C, the input impedance Z in, and part D, the output impedance ZO. Let's work through each one. Let's derive the current gain ratio AI. We start from the two defining H parameter equations for the common base model. VEB equals HIB times IE plus HRB times VCB and IC equals HFB times IE plus HOB times VCB. Since the output current IL is simply the negative of the collector current IC and VCB equals IL times RL, which is the same as negative IC times RL, we can substitute this back into the equation for IC. That gives us IC equals HFB times IE minus HOB times IC times RL. Rearranging IC plus HOB times IE times RL equals HFB times IE thanks to RL. Rearranging IC plus HOB times IE times RL. Factoring out IC and dividing through, we get IC over IE equals HFB divided by 1 plus HOB times RL. Note the current gain AI is defined as IL over IE, which is the same as negative IC over IE. So AI equals negative HFB divided by 1 plus HOB times RL. Plugging in our numbers, negative 0.99 divided by 1 plus 8 times 10 to the negative 7 times 20 times 10 cubed, that works out to a current gain of 0.974. Notice that this is less than 1. The common base configuration does not provide current gain. In fact, it slightly attenuates the current. That's an important defining characteristic of this configuration. Next, let's find the voltage gain ratio, AV. We already know that IC over IE equals HFB over 1 plus HOBRL and that VCB equals negative IC times RL. Substituting the first into the second gives us VCB equals negative HFBRL over 1 plus HOBRL, all multiplied by IE. Now we need an expression for VEB in terms of IE. Starting again from VEB equals HIB times IE plus HRB times VCB. We substitute in our expression for VCB, VEB equals HIB times IE minus HRB times HFBRL over 1 plus HOBRL times IE. Factoring out IE, we get VEB equals IE times the quantity HIB times 1 plus HOBRL minus HFB HRBRL all over 1 plus HOBRL. The voltage gain is defined as AV equals VO over VI, which here is VCB over VEB. Dividing our two expressions and simplifying, we arrive at AV equals negative HFBRL divided by HIB plus RL times the quantity HIB HOB minus HFB HRB. Substituting our typical values in, we get AV equals negative 0.99 times 20 times 10 cubed divided by 30 plus 20 times 10 cubed times the quantity 30 times 8 times 10 to the negative 7 minus negative 0.99 times 4 times 10 to the negative 6. That works out to a voltage gain of 647.9. That's a very high voltage gain, and notice it's positive, which tells us something important. There is no phase inversion between input and output in a common base amplifier, unlike the common emitter configuration. Now let's determine the input impedance Z in. We start once more from VEB equals HIBIE plus HRBVCB. We already derived that VCB equals negative HFBRL over 1 plus HOBRL times IE. Substituting that in, VEB equals HIBIE plus HRB times negative HFBRLIE over 1 plus HOBRL. Simplifying, VEB equals HIBIE minus HRBHFBRL over 1 plus HOBRL. Simplifying, VEB equals HIBIE minus HRBHFBRL over 1 plus HOBRL. Since Z in is defined as VEB over IE, dividing through gives us Z in equals HIB minus HRBHFBRL over 1 plus HOBRL. Plugging in the numbers, 30 minus 4 times 10 to the negative 6 times negative 0.99 times 20 times 10 cubed all over 1 plus 8 times 10 to the negative 7 times 20 times 10 cubed. That gives us Z in equals 30.08 ohms. That's a very small input impedance, exactly the low input impedance we'd expect from a common base amplifier. And it's why this configuration is so well suited to low impedance signal sources. Finally, let's find the output impedance, the ZO, to find an output impedance. The standard approach is to set the input signal source to 0 and look back into the port we are interested in. In this case, the collector port, setting Vs to 0 means VEB becomes 0 as well. So effectively the input port is short circuited for a C, starting from IC equals HF BIE plus HOB VCB, and knowing that with VEB equal to 0, HIBIE equals negative HRB VCB, we can solve for IE equals negative HRB over HIB times VCB. Substituting this into our expression for IC equals HFB times negative HRB over HIB times VCB plus HOB VCB, simplifying IC equals VCB times the quantity HOB minus HFB HRB over HIB. The output admittance YO is defined as IC over VCB, so YO equals HOB minus HFB HRB over HIB. Plugging in our values, 1 divided by 8 times 10 to the negative 7 minus negative 0.99 times 4 times 10 to the negative 6 divided by 30. That gives us ZO equals 1.07 megohms, a very large output impedance. Again, exactly what we'd expect from the common base configuration. One more thing worth noting, ZO here is actually decreased slightly compared to what you'd get from HOB alone because of the feedback from the output mesh back to the input mesh through HRB VCB. It's a small effect, but it shows that the parameters aren't fully independent of each other. Let's bring it all together. Based on the typical values we used in this example, we can summarize the characteristics of the common base amplifier as follows. First, the current gain is less than 1. We calculated 0.974. So this configuration does not amplify current. Second, the voltage gain is high, 647.9 in our example. Third, the power gain is approximately equal to the voltage gain. Since the current gain is close to 1, we calculated 631.1. Fourth, there is no phase shift for either current or voltage. The output signal is in phase with the input, which is a key distinguishing feature of the common base configuration compared to the common emitter configuration. Fifth, the input impedance is small, 30.08 ohms in our example. And sixth, the output impedance is large, 1.07 megohms. Put together, these characteristics tell you exactly when to reach for a common base amplifier. Whenever you need a stage with high voltage gain, no phase inversion, a very low input impedance to match a low impedance source, and a high output impedance to hand off to the next stage. That wraps up our analysis of the common base amplifier. Thank you.